All right, so this is, we're going to kind of try to finish up 5.2. So this is actually problem number 13 in 5.2, number 13. So again, we want to find zeros. So how do we find zeros? We need to at least find one zero and generate the factor associated with it, and then divide that in to remove it to see what's left, and then go on from there. Also remember, we're going to make really good use of the graphing calculator. So you might say, well, hey, I don't have a TI-84. Well, download the TI-84 app on your phone, get used to using the TI-84 to speed things up, and then when you get to the test, just check out a TI-84 at the testing center. Okay? All right, so let's go ahead and begin. First of all, what are the possible rational zeros? A zero, remember, is a value of x that makes the function become zero. So my possible rational zeros are going to be what? Factors of the constant term divided by factors, that's supposed to say factors, of the leading coefficient. So factors of the constant term is negative 20. So what are the factors of negative 20? Well, plus or minus 1 goes into 20, right? Plus or minus 2, plus or minus 4, plus or minus 5, and plus or minus 10, and plus or minus 20. That's a lot of stuff. How about factors of the leading coefficient of 4? Plus or minus 1, plus or minus 2, and plus or minus 4. Now notice, one thing we could do is, in this particular problem, we could write this as 4 times x cubed minus 6x squared plus 6x minus 5. In other words, I could factor out a 4 out of the beginning, okay, to make life a little easier, okay? That actually might benefit me. Why? Because now if I look at the rational zero theorem here, it becomes pretty clear what to expect. The rational zero theorem here on this guy would be the factors of the 5. What goes into 5? Plus or minus 1 and plus or minus 5. My new leading coefficient is now 1. What goes into that? Plus or minus 1. Okay? So in this case, I either a 1 or a negative 1. This leaves me with either 1 or negative 1 or 5 over 1 or 5 over negative 1. So 5 or negative 5. There's only 4 numbers to check. Okay? To see what if there is a rational zero, it will be in this list. It will be one of these 4 numbers. Okay? So let's check it real quick. So I'm going to go to y equals and put in the function. Okay? Now I put in the original function, so let me clear this out. We'll put in the reduced function. The reduced function is what? X to the power 3 minus 6x to the power 2. Whoops. Sorry about that. X to the power 3, get out of the power. That's an easy mistake to make. Minus 6x to the power 2 plus 6x minus 5. Now, if you get a version that does not have this is what's called the greatest common factor of the whole polynomial, this 4 that I pulled out. If you have, if you don't have a number that divides into all the different terms, that's okay. Just leave it the way it was originally. You'll just have a bigger list of possible rational zeros. That's okay. All right? So go ahead and put in either the original function or the reduced version if yours does reduce. Some do, some don't, depending on what randomization you get. And now, to make a table, let's go to table set. To look for whole numbers. Both of these would be whole numbers. 1 over 1 and 5 over 1 would be whole numbers. So I just want to make sure I'm starting at 0 and going by 1 so that I'm plugging in whole numbers. Generate a table. So notice at 5, I'm getting a 0. Okay? 5's on my list. What about at 1? No. How about negative 1 and negative 5? Negative 1 is not a 0. Negative 5 is not a 0. But 5 is a 0, right? So we're good. Okay? My 5 is a 0, so it is on the list. So what do we know? We therefore know that x equals, I guess we'll use a different color here. We therefore know that x equals 5 is a 0, so therefore x minus 5 is a factor. So I want to see what's left over. So to see what's left over, let's do a long division, okay, or a synthetic division. So I'm going to divide x minus 5 into this polynomial. So x minus 5 into 4x cubed. Now, we can either divide, remember, we've rewritten this as 4 times x cubed minus 6x squared plus 6x minus 5, right? I divided 4, I pulled a 4, I factored a 4 out of each term, right? Pulled it away from the first term, pulled it away from the second term, pulled it away from the third term, pulled it away from the fourth term. So we can just deal with, there's already a 4 on the outside of the problem, okay? I'm just going to deal with this part. If you did not pull out a greatest common factor, then you don't have to worry about that. Just put your original polynomial here. I'll just use the reduced one. Okay, so how do I do this? How do I make an x look like an x cubed? I only need 2 more x's, right? 2 more powers of x, so I end up with x cubed minus 5x squared. Subtract. What do I get? I get x cubed, take away x cubed is gone. Negative 6 plus 5 gives me negative 1. How do I make an x look like a negative 1x squared? With a what? With a negative 1 and another x. Negative 1x times x, negative 1x squared. Negative 1x times negative 5 is plus 5x. Subtract, because that's been accounted for. And we end up with 1, negative 1 plus 1 is gone. 6, take away 5, leaves me with 1. And so how do I make an x look like an x? I need to multiply by what? A 1, a positive 1. 1 times x is x. 1 times negative 5 is negative 5. Subtract. And we see that we do indeed get a remainder 0, which we better get. Otherwise, we didn't really have a factor. Okay, that's supposed to be a smiley face because we got a 0. Okay, so therefore, this polynomial can be written. So basically what I've got now is I have a new factorization that looks like a 4 on the outside that we pulled out times an x minus 5 times x squared minus x plus 1. Okay? Now, is this fully factored? Do I know all the zeros? No, I still only know one zero, the 5. To see the other zeros, I have to figure out how this guy factors. And if you try to factor this by hand, you'll discover it doesn't factor by hand, which means we're going to have to use the quadratic formula. Yay, right? So for the quadratic formula, my a is 1, because it's the coefficient of the x squared. My b is negative 1. My c is 1. Okay, so let's use the quadratic formula, our favorite thing, right? So I'm going to have x is equal to, and again, we're doing the quadratic formula just on this quadratic right here, not on the whole thing. So my x is negative of the b plus or minus root b squared, negative 1 squared minus 4 times the a times the c, whole thing divided by 2 times the a, which is going to be 1 plus or minus root of, negative 1 squared is 1, 1 take away 4 is 3. Okay, now how do you deal with root of negative 3? That's going to be root of negative 1 times 3. Whoops. Okay, which is what? Root negative 1, root 3. We peel off the negative 1. And remember, root of negative 1 is I, so it's I root 3, or root 3i. So this is going to be 1 plus or minus root 3i. We like to put the I at the end, over 2. And so this is not in what's called a plus bi form. Okay, in a plus bi form, it would be, I guess I'm running out of room here, but in a plus bi form, this would be 1/2 plus or minus root 3 over 2 times I. Okay, because I'm going to split this into 2 fractions. So this generates 2 different zeros. Okay, so what are my zeros? My first 0 was the 5, right? So my zeros were, in this case, were 5, 1/2 plus root 3 over 2i, and then 1/2 minus root 3 over 2i. That's a root 3, sorry about that. Okay, so these are my 3 zeros. A 0, a 0, and a 0. I'm just kind of boxing them in so you kind of see, but we put commas between them. Okay, and that's it. So it's a little bit of a messy problem because we end up with complex numbers as roots here. Okay? All right. So now, what if they wanted the factorization? If they wanted the factorization, I'd still have to deal with that 4. Okay? So basically, what I could do is I could distribute the 4 back into any one of the factors. So they're not asking for the factorization, but if they did, right now what I've got is I've got 4 times x minus 5 times x, take away, parentheses, 1/2 plus root 3 over 2i. And then x take away, parentheses, 1/2 minus root 3 over 2i. That's my factorization right now with a 4 factored out front. Typically, we don't leave a constant number. Often what we'll do is we'll put that into any one of the factors. Don't put it into all 3, because then you're multiplying by 4 and 4 and 4. You'd be multiplying by 64. Just put into any one of the factors. I'd probably rewrite this as a 4x minus 20 or something. Okay? Or you could leave it like this, but if they're looking for, if they don't want a constant number out front, a constant number factor, you could think of this as a 4x minus a 20 if you like. Okay? But they're not asking for the factorization. They're just asking us for the 3 zeros of the function. Okay? And there we go. And I knew there's going to be 3 zeros because it's a degree 3 polynomial. All right, let's go on. Okay, this is number 14. Number 14 is probably the toughest one in the batch of all these different problems that we've been doing. Because it's a 4th degree, and also it's suggesting that we might get some non-real factors, which it looks like we will. Okay, so it's going to be a little bit tricky. So the first thing we do is what? Is there a GCF I could factor out to make life simpler? Well, let's see. 4 goes into 28. That's good. 4 does not go into 50, though. How about 2? Can I pull a 2 out? 2 times what's left over. I'm going to have 2x to the 4th plus 14x to the 3rd plus 25x squared plus, what do I have, 28? X plus 15. So that's going to make life a little easier. At least the numbers are a little smaller. Okay, less chance of a mistake. Let's just double check. 4, 28, 25, 56, and 2 times 15 is 30. So that looks good. All right, so I'm just going to worry about this slightly reduced polynomial now. We've factored out a GCF of 2. So anything that makes the original polynomial 0 would also make this reduced guy 0, and vice versa. So how do we proceed? Well, we need, hopefully, to find some zeros. Okay, so let's look at the rational zeros theorem. So my potential rational zeros are going to be what? Factors of the 15. So 1 goes into 15, 3 goes into 15, 5 goes into 15, and 15 goes into 15 over factors of the 2 on the inside here. Okay, plus or minus 1, plus or minus 2. So that means my rational zeros are going to either be whole numbers because of 1 on the bottom, or halves. And I can check for both of those using the calculator very easily. Okay, so first let's look for whole numbers. How do I look for whole numbers? You should know this by now. And by the way, if you're doing this without the calculator, you're making way extra work for yourself. Download the app on your phone, get used to using it, and then check out a calculator on test day. Okay? Now, let's go to y equals, put in the function. I'm going to put in the reduced function because I'm looking for zeros of the reduced function. They will also be zeros of the original. Okay? Because if something makes all of this equal to 0, it'll make 2 times it also equal to 0, because 2 times 0 is still 0. All right, so let's go ahead and put in this reduced function. I have 2x to the power 4. Let's get out of the power. Plus 14x to the power 3. Get out of the power. Plus 25x to the 2. Use the x to the 2 shortcut button. Plus 28x plus 15. Okay, there I go. Bam. Now let's go to table set. Make sure we're set up for whole numbers. For whole numbers, we're going to start at 0 and go by ones. Let's make a table. So I don't see any zeros in the positive region. How about in the negative region? Okay, -1 is a 0. and so is negative 5. I saw two of them, negative 1 and negative 5. They're both on this list, right? Negative 1 over 1 and negative 5 over 1. Right, so this is a negative 5, and this is a negative 1. Those turned out to be zeros. They're in my list, okay? The other ones were potential rational zeros. Now, what about halves? Could there be some halves that are zeros? If there are, it'll speed things up because I got to find 4 different zeros. That's a lot of work, all right? Could the halves, how would I check halves? Why am I going to check halves? Because I see there's a 2 on the bottom. When there's a 2 on the bottom, that means we're plugging in halves. How can I check some halves? Table set, remember how to do this? Start at 0 and make your delta table by 1/2. So 1 divided by 2. Okay, table. And let's scroll in the positive region. I'm not seeing any zeros there. How about in the negative region? Well, I see the 0 at negative 1, but I care about the halves, the ones that end in 0.5. This is negative 1/2, this is negative 3/2. I'm not seeing any additional zeros here. Okay, I see my 0 at negative 5. The very last choice would be 15/2, which would be 7.5. And I don't see that as a 0, so I know I'm done looking. So there's no more zeros, just no more rational zeros. There's just these two. So negative 1 and negative 5. Okay, so let's clear some space here. Okay, so what we've done is we found that we first factored this, factored out of 2. And so that's 2 times what? 2x to the 4th plus 14x cubed plus 25. X squared plus 28x plus 30. And then we found that x equals negative 1 and x equals negative 5 were zeros. Okay, and so just double checking here. There's the negative 5, the negative 1, yep. So therefore x minus negative 1 is a factor, and which means x plus 1. And x minus negative 5 is a factor, which means x plus 5. Okay, now I need to pull those out of the polynomial to see what's left. I could do a long division with x plus 1 to pull that out and then do another long division with x plus 5, but as we saw last time, we could just multiply those together and then do one big long division. Okay, why does that work? Remember the example we looked at? Suppose, let's just go back to the world of numbers for a minute. So in number world, let's just look at numbers for a minute because it's easier to come sometimes to see factors with just numbers. What if I had like 2 times 3 times 5 times 7? 2 times 3 is 6. 6 times 5 is 30. 30 times 7 is 210. Suppose someone tells me, someone gives me the number 210, and they tell me, you know what? 2 is a factor and 3 is a factor. Divide those out. Well, I could do 2 into 210. Divide that out. What would I get? 105, right? And then I could do 3 into 105 and get what? 35. Okay? That's 2 long divisions. Could I do it? Could I get to the 35 in one step? Yes, I could take the 2 times the 3, the 2 zeros that I know. If someone tells me 2 is a 0 and 3 is a 0, that means they multiply to 6. Okay, so I could do 6 into the original 210, and I'm going to get out 35. Okay, same result. In other words, I do one division. That's a lot easier. The idea is if you multiply if you have to divide out 2 different factors, multiplying together and just do one division. That's the idea. So the x plus 1 times x plus 5 are my factors. So let's go ahead and multiply them. So now x plus 1, whoops, turn the pen back on. X plus 1 and x plus 5 are both factors. So if I FOIL those out, what do I get? X squared plus 5x plus 1x plus 5. So that is, so that is x squared plus 6x plus 5 is a factor. So I'm going to divide that into the polynomial. Remember, my polynomial reduced to 2 times 2x to the 4th plus 14x cubed plus 25x squared plus 28x plus 15, right? So that's the polynomial I'm going to use. The 2 on that extra 2 is not going to affect what the zeros are. It's just easier to work with the smaller numbers. So I'm going to take x squared plus 6x plus 5 and divide it into all of this stuff. 2x to the fourth plus 14x cubed plus, and that's a 14, sorry. It's a little ugly looking 14. Plus 25x squared plus 28x plus 15. Divide that in, okay? So how do I make an x squared look like a 2x to the fourth? I need another 2 and 2 more x's, 2 more powers of x. Okay, so 2 times 1 is 2, x to the fourth. 2x squared times 6x is 12, x to the third. And 2x squared times 5 is 10, x squared. Okay, subtract all of this. What do I get? 2x to the fourth, take away 2x to the fourth is gone. 14, take away 12 leaves me with 2 of those guys. 25, take away 10 leaves me with 15 of those guys. And then bring down the 28x and the 15. Oops, that's a 15, sorry. Let me squeeze that in there. Okay. Now, how do I make the first term on the outside look like the new first term on the inside? And the answer is, I need to multiply by what? I need to multiply by a 2 to make the numbers match. 2 times 1 is 2, and I need one more power of x. 2x times x squared becomes 2x cubed. 2x times 6x becomes 12x squared. 2x times 5 becomes 10x, and I'm going to subtract because it was accounted for. And so what do we get? We get 2x cubed, take away 2x cubed is gone. 15 take away 12 leaves me with what? 3x squared. 28 take away 10 leaves me with what? 18x. And 15 take away nothing leaves me with 15. How do I make an x squared look like a 3x squared? I multiply just by a 3. 3 times x squared is 3x squared. 3 times 6x is 18x. 3 times 5 is 15. Subtract because it was accounted for. And I end up with, yay, remainder 0. Happy, happy, right? Why are we happy? That's supposed to be a remainder 0, a happy remainder 0, because that means this was indeed a factor and we did a correct long division. Okay? So, we can now rewrite this polynomial as what? We can now write this as a 2 times an x squared, well actually an x plus 1 and an x plus 5, which is what built this, but I used it in the foiled out form when I did the division, so I only had to do one division. But I'm going to write it in the factored form because we're looking for factors. Okay, we're actually looking for zeros, but each factor results in a 0. So now the last factor we have is this quotient that we got, this result from the division, 2x squared plus 2x plus 3. Now how do we deal with that? If you try to factor that by hand, you'll discover it does not factor. So we have to use quadratic formula. Okay, so when we use quadratic formula here, we know my A and my B and my C, right? My A is 2, my B is 2, my C is 3. Okay, for quadratic formula, so we end up with what? X equals, on this guy, x equals negative b plus or minus root b squared, so that's 2 squared, which is 4, minus 4 times 2 times 3. 4 times a times c. 4 times 2 times 3. 4 times 2 is 8. 8 times 3 is 24, right? All divided by 2a, which is 2 times 2, which is 4. Okay, so this is going to be negative 2 plus or minus root negative 20 over 4. Now, what's root negative 20? I'm kind of running out of room here, but we can think of root negative 20 as root of negative 1 times 20, which is root negative 1, root 20. Okay, so what is root negative 1, root 20? I guess sorry about this, but I'm going to have to kind of finish the work up in this area. So I have root negative 1, I'll just rewrite it, root negative 1, root 20. That's going to be, root negative 1 is I. Now the root 20, I could think of root 4, root 5, because 4 is a perfect square. So that's going to be an I times a 2 times a root 5, or I could write it as 2 root 5 I, because we like to put the I at the end. Okay? So I end up with Let me kind of change colors here. So we end up with my quadratic formula here ends up with -2 plus or minus 2 root 5I all over 4. Now, of course, what I can do is I cannot cancel the 2 with the 4. Don't be tempted to do that. You can never cancel anything that's either adding or subtracting or plus minusing to anything else. Okay? Only multiplication can be canceled. So I can rewrite that as, I guess let me kind of finish it over here. We're looking for empty space. We can factor out a 2. So I'll factor out a 2, and then I have -1, because that's really when you factor a 2 out, think of this as a 2 times a 1. Okay, so when I factor a 2 away, I'm left with -1 plus or minus root 5I all over 4. The 2 and the 4 reduce to 1 and 2. So I end up with -1 plus or minus root 5I over 2, which means what? -1/2 plus root 5 over 2I, and -1/2 minus root 5 over 2I. So those are the additional 2 zeros of the function. Okay, they want the zeros here, not the factors. Okay, so those are my zeros. So my zeros would be, let's remember what the zeros are. The zeros would be -1 from here, -5 from here, and then these 2 complex number zeros. Pretty ugly, right? Let's clear a little bit. Let's also write out the factorization just for practice on that. So what were my zeros? My zeros were -1, -5, -1/2 plus root 5 over 2. Whoops, sorry about that. Root 5 over 2I, and then -1/2 minus root 5 over 2I. Those are my 4 zeros, so that's what I would put in the answer box. But what about if they ask me for the factorization, what would be the factorization? Okay, well, remember that we had a 2 on the outside, and then we had x take away -1, x take away -5, x take away, parentheses again, -1/2 plus root 5 over 2I, and x take away, parentheses, -1/2 minus root 5 over 2I. Okay, and now I'm going to distribute the minus into those negatives. And so what do I get? Let's change colors here a little bit. So I end up with a 2 times x minus -1 is x plus 1. X minus -5 is x plus 5. X, take away all this stuff, is x plus 1/2 minus root 5 over 2I, because the minus is going to make this positive and this negative. And here the minus is going to make this positive positive. So x plus 1/2 plus root 5 over 2I. That would be the factorization. Okay? Yay, right? Wasn't that fun? Okay, notice I get 4 factors, which means I get 4 zeros. Right? Each factor gives me a 0. Here are the zeros associated with the factors. This is 2 is a GCF, a greatest common factor. This does not result in an additional 0 because there's no way to make 2 equal to 0. Right? Only things with x's can equal 0. A 2 is never going to be a 0. And that's it, right? So that's a good problem. That's probably the hardest problem in the batch. The remaining ones, like 15, 16, and 17, are similar to this, but not as complicated because they don't have as high of a power. All right, so I guess we'll end the presentation here, and you guys should be able to figure out the remaining ones. That'll be good practice for you. Okay, and that'll let you know if you really know this stuff or not. Very similar to this one. Okay, again, just not, the powers are just not as high on the remaining ones. I'm just going to kind of take a quick look at the remaining, my other screen here. I got, let's see, an x cubed, an x cubed. Yeah, the remaining ones are just x cubes, so there should be a lot easier. Okay. Whoops, hang on. My bad. And that's it. All right, so we should be good here.